You think you choose when you go to sleep. You think that if you just lie down and close your eyes, you are in control. But the truth is, you have almost no say in the matter. Right now, at this very second, there is a silent biological war happening inside your brain between two opposing forces. One is trying to keep you awake at all costs, and the other is slowly poisoning you into unconsciousness. Until you understand these two forces, process C and process S, you will never truly master your energy, your focus, or your health. Today, we aren't just giving you tips. We're looking under the hood of human biology to explain exactly how your brain decides when it's time to shut down. Welcome back. In our previous deep dive, we answered the fundamental question, what is sleep? We explored the architecture of sleep stages, from the restorative depths of delta waves to the emotional processing of REM. If you haven't seen that video, I highly recommend checking it out for the foundation. But today, we are pivoting from what sleep is to how sleep happens. Have you ever wondered why you can feel absolutely exhausted at 2 p.m., struggle to keep your eyes open, but then suddenly catch a second wind at 9 p.m., feeling wide awake just when you should be winding down? Or why, no matter how tired you are, you can't seem to sleep in on a Tuesday morning? The answer lies in the interaction between two distinct biological systems. Scientists call this the two-process model of sleep regulation. It is the governing law of your wakefulness. By the end of this video, you will understand the intricate dance between your internal clock and chemical pressure, and you'll know exactly why that cup of coffee at 4 p.m. is destroying your recovery. Let's begin with the first combatant in this war, process C, or the circadian rhythm. The term circadian comes from the Latin circa, meaning approximately, and dies, meaning day. This is your internal biological clock. But where is it? It's not just a metaphorical concept. It is a physical, tangible structure in your brain called the Suprachiasmatic Nucleus, or SCN. The SCN is arguably one of the most fascinating pieces of hardware in the human body. Located within the hypothalamus, directly above the optic chiasm, where your optic nerves cross, this tiny region contains roughly 20,000 neurons. That might sound like a lot, but in the context of the brain, it is the size of a grain of rice. Yet, this grain of rice acts as the conductor for the entire orchestra of your biology. The SCN oscillates on a cycle that is slightly longer than 24 hours, usually around 24 hours and 15 minutes. Its job is to coordinate every cell in your body. You see, you don't just have one clock. Every organ, your liver, your heart, your gut, has its own peripheral clock. The SCN is the master synchronizer that ensures your liver knows its daytime and your heart knows its night. Without the SCN, your bodily functions would drift into chaos. But how does the SCN know what time it is? It needs a signal. In chronobiology, we call these signals zeitgebers, a German word meaning time givers. The most powerful zeitgeber is light. Here is the mechanism. When light enters your eye, it doesn't just hit the rods and cones that allow you to see shapes and colors. It strikes a special set of cells called intrinsically photosensitive retinal ganglion cells. These cells contain a photopigment called melanopsin, which is highly sensitive to blue light frequencies. When blue light hits these cells, they send an electrical signal directly down the retino-hypothalamic tract to the SCN. This signal tells the SCN, it's daytime, be alert. In response, the SCN suppresses the production of melatonin and stimulates the release of cortisol, epinephrine, and serotonin to keep you alert and your body temperature high. This is why getting sunlight in your eyes first thing in the morning is the single most effective way to set your clock. Speaking of morning habits, I'm curious, are you checking your phone the second you wake up, or do you get actual sunlight first? It makes a huge difference to your SCN. Type sunlight or screen in the comments below so we can see how many of us are fighting our biology. Conversely, when darkness falls, the lack of light signals the SCN to take its foot off the brake. It signals the pineal gland to begin secreting melatonin. Now, there's a massive misconception about melatonin. People think of it as a sleeping pill. It is not. Melatonin is a hormone of darkness. It does not generate sleep. It signals to the body that it's the time for sleep. It's like the starter pistol at a race. It starts the event, but it doesn't run the race for you. This circadian rhythm is robust. It pushes you to be awake during the day and asleep at night, regardless of how tired you feel. This is why shift work is classified by the World Health Organization as a potential carcinogen. When you fight the SCN by looking at bright lights at 2 a.m. and sleeping in a dark room at noon, you are creating a state of circadian misalignment. Your metabolic organs are preparing for food while your brain is trying to sleep. It is psychological anarchy. However, the clock is only half the story. If the clock were the only factor, you would never feel more tired after a workout than after sitting on the couch. This brings us to the second combatant, process S, or the homeostatic sleep drive. While process C is a wave that goes up and down, process S is a linear climb. It represents sleep pressure. Think of this like a balloon filling with air or an hourglass filling with sand. From the moment you wake up, you begin accumulating sleep pressure. The longer you're awake, the greater the pressure becomes, and the sleepier you feel. When you sleep, you release the pressure, emptying the balloon so you can start fresh the next day. But what exactly is this pressure? It's not magic, it's chemistry. The star of this show is a molecule called adenosine. To understand adenosine, we have to look at energy. Every cell in your body runs on a fuel called ATP, adenosine triphosphate. As you go about your day, thinking, moving, exercising, your brain burns through massive amounts of ATP. As ATP is broken down to release energy, it loses its phosphate groups and leaves behind the backbone molecule, adenosine. This means that adenosine is literally the chemical waste product of being awake. As the day progresses, adenosine builds up in your brain. It floats around and binds to specific adenosine receptors in your neurons. When adenosine docks onto these receptors, it inhibits neural activity. It slows you down. It tells the brain, we have burned a lot of fuel. We need to stop and recharge. This accumulation happens constantly. By the time you've been awake for 16 hours, the concentration of adenosine is high enough that the urge to sleep becomes overwhelming. This is the psychological hunger for sleep. Before we talk about how we accidentally sabotage this process, I want to know, how many hours are you typically awake before you feel that first heavy wave of exhaustion? Is it 12 hours? 16 hours? Let me know your average awake time in the comments. Now, we have to talk about the elephant in the room, caffeine. Most people think caffeine gives you energy. This is false. Caffeine contains zero energy. It does not provide fuel. What caffeine does is much more devious. If you look at the molecular structure of caffeine, it looks incredibly similar to adenosine. Because of this structural mimicry, caffeine can slide into the adenosine receptors in your brain. But unlike adenosine, caffeine doesn't slow down the cell. It just sits there, blocking the receptor. It's like putting a piece of gum in a keyhole. The key, adenosine, can't get in. So while the caffeine is blocking the receptors, your brain doesn't sense the adenosine buildup. You feel alert, but here's the danger. The adenosine doesn't go away. It continues to build up in the background, waiting for that caffeine to wear off. This is the mechanism behind the famous caffeine crash. Once your liver metabolizes the caffeine and the receptors open up, that massive tidal wave of accumulated adenosine rushes in all at once. You don't just return to baseline tired. You are hit with hours of suppressed fatigue instantly. Furthermore, caffeine has a half-life of roughly 5 to 7 hours. If you have a coffee at 4 p.m., by 10 p.m., half of that caffeine is still active in your brain, blocking the sleep signals just as you're trying to wind down. This is why you might fall asleep but struggle to get deep restorative sleep. Process S is being chemically hacked. Now, let's put these two pieces together. This is where the magic and the misery happens. The two-process model is the superposition of the circadian rhythm, process C, and sleep pressure, process S. Imagine a graph. Process S, sleep pressure, starts low in the morning and rises steadily all day, peaking right before bed. It wants you to sleep more and more as the day goes on. Process C, the circadian wake drive, acts as a counterforce. Interestingly, the circadian alerting signal is actually quite weak in the morning because sleep pressure is low, so you don't need much help staying awake. But as the day progresses and adenosine builds up, the circadian clock ramps up its wake-up signal to fight the fatigue. This is why you don't just slowly get more tired until you collapse. The circadian rhythm props you up against the rising tide of adenosine. However, there are two critical points in this curve that explain your daily energy levels. First, the postprandial dip, the afternoon crash. Around 1 p.m. to 3 p.m., there is a natural biological dip in the circadian alerting system. At the same time, adenosine has been building for about 7 or 8 hours. The combination of rising sleep pressure and a momentary drop in the wake drive signal creates that overwhelming urge to nap in the mid-afternoon. It's not just because you ate a heavy lunch, though that does contribute. It is an evolutionary feature of human biology. Second, the forbidden zone. This is the phenomenon where you feel surprisingly alert around 8 p.m. or 9 p.m., even if you were tired earlier. Right before the SCN prepares for sleep, it sends out a final, strong surge of alerting signals to keep you awake until the very end of the day. This is often called the second wind. If you miss your sleep gate, the moment when the signal drops off and melatonin rises, you might find yourself lying in bed exhausted but unable to sleep because you are stuck in this high alert zone. Finally, the sleep gate opens. Ideally, around 10 p.m. or 11 p.m., two things happen simultaneously. 1. The circadian alerting signal plummets. Melatonin rises. 2. Adenosine pressure is at its absolute peak. When these two align, the urge to sleep is irresistible and the transition to unconsciousness is rapid. During the night while you sleep, the adenosine is cleared away and process S strips. Meanwhile, the circadian rhythm hits its lowest point of alertness around 4 a.m., lowest body temperature. Here's a fascinating realization regarding waking up. Why do you wake up in the morning? It isn't just because you're done resting. You wake up because process C, circadian rhythm, begins to rise and release cortisol, and process S, adenosine, has been depleted. The pressure is gone, and the engine is revving up again. This explains why social jet lag is so destructive. If you stay up until 2 a.m. on the weekend, you are delaying the clearance of adenosine. You then sleep in until 11 a.m. But your SCN, process C, woke up at 7 a.m. because of the light. You have desynchronized the two processes. You wake up feeling groggy, a phenomenon called sleep inertia, because even though you slept enough hours, you woke up at the wrong biological time. Understanding that sleep is not a simple switch, but a complex negotiation between these two processes changes how we treat our bodies. We realize that pulling an all-nighter doesn't just make us tired, it leaves high levels of adenosine in the brain that interfere with cognitive function for days. We realize that viewing light at night isn't just a bad habit, it is a direct suppression of the psychological trigger required to close the sleep gate. Sleep is not a passive state. It is a highly active, regulated biological imperative controlled by the rhythm of the sun and the chemistry of your cells. To master it, you must respect the clock and manage the pressure. If you found value in understanding the biology of your brain today, please make sure you are subscribed. This series is only going to get deeper, and I don't want you to miss the practical application in the next episode. Click the subscribe button and the notification bell right now. If you want to support the channel, leave a like, and if you have a friend who drinks coffee at 8 p.m. and complains about insomnia, share this video with them. See you in the next one. Sleep well.